Hello and good morning everyone. Today inshallah we will continue differentiability and good news, we will finish this part and we will enter inshallah for the second lecture the antiderivative or integration. This at the time being, as you can see, this is our study plan. In the time being we are at the probabilities of differential functions. This is our second lecture in this part. And hopefully today we will finish it inshallah. And as I told you, I will try as much as possible to go into direct antiderivatives, and we will do a lot inshallah in the next week. Hopefully we will be able to finalize it inshallah, and then we will go to the analysis of the different integration areas and the Cauchy with FTC, as you can see. Okay, of course our notes, references, you will find them in Moodle, and also the recorded lectures, most of them, or all of them, you will find them on the YouTube, starting from the beginning of our course till the end, inshallah. Today, as I told you, I will go to continue derivatives and we will go through properties or applications. I would rather like to call it applications on the derivative, okay? We will go through rules theory, and which is actually an introduction to the optimization down the road. Cauchy's rule, which sometimes we call it Total rule. It's a very good method to help you to deal with various types of limits. The type of limits which is really complicated, it will make your life much easier. Also, we will go through the differentiability in vector functions, vector valued functions, the operations with differential functions, the addition, the subtraction, and the multiplication, differentiability and continuity, what's the relation connecting both of them together, either in R or in Rn or in vector valued function, differentiability and the partial derivatives. Those parts from 5 till 7, it's like a summary of what we did go through previously with the main theories that you will need. Then finally we will define the CK functions, and this is for our agenda today. Let's start with rules either between 1652 up to 1719, and rules theory is really a very nice theory. It states that if you have f such that the domain is apart from R into R. So I'm talking about functions in in one variable, single variable functions I mean. Be a function which is continuous in AB and differentiable. So how many conditions do I have? 2 of them, continuous and differentiable. In the open interval AB. And look, the third condition, that the value of the function at the beginning of the period equal the value of the function by the end of the period. If these conditions happens, then you will have a certain value which is C belongs to this interval, where at C you will have f dash C equal to 0. Which means if you have a function f which is continuous, differentiable on a certain interval AB, and the value of this function at the beginning and at the end, as you can see, they are equal to each other, then there is a must that you will have C belongs to this interval where f dash C is equal to 0, like this guy or like that. Remark, if any of the conditions, that means continuity, differentiability, or f of A doesn't equal to f of B are broken, then you can't apply the rules theory, or to be sure that the rules theory really exists. So once more, it's not enough that the function is continuous. It has to be differentiable in AB. If it is only continuous, we cannot apply rules theory, and so there is no certain point at which you will find f dash C is equal to 0. That's mainly what rules theory is telling us. The corollary, it has 2 corollaries, will help us down the road in searching for optimality, as I told you. The first of them is between 2 zeros of a differentiable function, there is at least 1 zero of the derivative. So if I have, as I told you, 2 zeros of the differentiable function, there is at least 1 zero of the derivative between both of them. The function is changing from positive to negative or vice versa, then you will have a point at which there is a zero for its derivative. Also, there is at most one, if you have, once more, between two consecutive zeros of the derivative of a differentiable function, there is at most 1 zero of the function, and this is also another method that we can use if we want to find a root for a function, depending on this reality. Okay. This is Cauchy's theory, which is really very important theory. It helps us, as I told you, to treat limits or complicated limits. And the theory is very, very simple. If I have a rational function, f of x over g of x, both of them are polynomials, and if you make the substitution and out of the undefined quantities, you know that we have 7 undefined quantities. Infinity minus infinity, infinity to the power of 0, 0 times infinity, 0 over 0, infinity over infinity, 1 to the power of infinity. Out of all of these undefined values, I will talk about just only 2 of them, which are 0 over 0 or infinity over infinity. If you have a limit and these are the values after you substitute, I can use Cauchy's theory, which states simply just differentiate the denominator by itself, and then differentiate the denominator by itself, then apply the limit. If the result is still 0 over 0 undefined or infinity over infinity, do once more a derivative for the denominator and the derivative of the denominator, same way like, then take the limit. So what I mean, if it is still 0 over 0, I can reapply it. So I can do limit x tends to a, then get f double dash of x divided by g double dash of x, then make the substitution. If it is still under one of the undefined quantities, these two, then apply it once more till you can simplify it, okay? And you can find the limit at this point. This is one of the best theories that you can use or rely on when you are searching for finding values of limits also. In order to make it easy on you, let's look to these problems. Those problems are direct substitution or direct interpretation for the evaluation. So if I look to this one, which is lim x over x to the power of 5, I have limit x which tends to infinity. This is lim of x divided by x to the power of 5. So simply, if you start substituting, you will find infinity over infinity. Since then, infinity is equal to infinity. I can now apply Rawls' theory. So simply, all I have to do is to differentiate the numerator and differentiate the denominator. So differentiating the numerator will give you 1 over x, and differentiating the denominator is going to be 5x to the power of 4. Don't substitute at the time being. Just my advice to you, just simplify it first, then start substituting. So as you can see, this is exactly like limit x tends to infinity. It's going to be 1 over 5x to the power of 5. Once you make a substitution, it's going to be 1 over 5 times infinity, which is 1 over infinity. And as you know, anything divided by infinity, the result is going to be 0, as you can see. So simply, I could skip the existence of the logarithmic function just by applying this rule. If I look to the second problem, which looks really very tempting, the second problem, you will have a limit of x tends to 0 for x times ln of x. And this problem by itself, if you start substituting, Muhammad, you will find it is 0 times ln over 0, which leads to 0 times infinity. I know ln 0 is equal to negative infinity, but still it's an undefined quantity, 0 times infinity. And unfortunately, I can't apply Cauchy's rule. But remark that I can use one of the advantages of the changing a defined value from a form to another. So simply, I can do the following. Let's put it in this way. Limit x tends to 0, and then I will have ln x divided by 1 over x. So all I did is I've tried to change the shape of my function. So instead of having x times ln of x, I will change it x. Instead of to be a denominator, it's going to be a denominator for the existing denominator. As you know the rule, denominator with denominator is a denominator, so I didn't change the problem. But the nice remark is once you substitute by 0, you will have ln 0 divided by 1 over 0, which leads to infinity over infinity. That's where I can apply Cauchy's theory once more. Let's apply it together. Let's differentiate the denominator and then the denominator and take the limit once more. So differentiating the denominator is going to be 1 over x. Differentiating the denominator will be negative 1 over x squared. Yes, you are right. Because simply, if I want to differentiate this guy, I will consider x to the power of negative 1. Yes. So differentiating simply will be negative of x to the power of negative 2, as you can see. Okay. Which is simply negative 1 over x squared. Don't substitute at the time being. Simplify it first, then make your substitution. So at this stage, I can rewrite it this way, Muhammad. Limit x tends to 0, and it's going to be negative x squared over x, which, as you can see, I can eliminate x with the power 2, and I will have the limit of x tends to 0 of negative x, which is simply equal to 0. Okay? But if you start differentiating or substituting at this point, it will be infinity over infinity. So it will lead to more or lengthy steps dealing with this problem, and it's not going to be as easy as you can see. Also, one of the very nice ideas that you can see is dealing with this problem. And it's a little bit complicated compared to the previous ones, but still it has a very nice relation or a very steps that will be repeated down the road if you know how to treat those types of functions. So simply, I have it's the limit of x tends to 0 of a 2x to the power of x. Of course, it's a 0 positive, but still it's a 0. So if I try to make the substitution, you will find it's a 0 to the power of 0, which is also one of the undefined quantities that I told you about. Yes, okay. Let's remember that we have some of the undefined quantities. This is one of them. 1 to the power of infinity, 0 power 0, 0 dot infinity, 0 to the power of infinity, and then 0 over 0 and infinity by infinity. Count them, 1, 2, 3, 4, 5, 6, and 7. So out of all of these 7 undefined values, I can use Cauchy once, or L'Hopital theory, once it is 0 over 0 or infinity over infinity. So all I have to do at the time being, just trying to make this guy logs to one of these. You have plenty of ideas, but one of them is really very tempting, which is, you know, about the fact that if I have x, for example, I can rewrite it e to the power of ln of x. They are both equal to each other. Okay, and the limit can go to the power or to the parts of your function. So instead of dealing with this function, I will deal with the equivalent form but containing the exponential and logarithmic part. So limit x tends to 0, and instead of dealing with this guy, I will deal with e to the power of ln 2x to the power of x. Okay? Okay, this form will help us a lot. So the second step, you know that I can put it on this form, e to the power of ln 2x times x. Am I right? Yes. Yes, of course. and the limit will be limit x tends to 0. Because the limit acts only on the part that contains x values. So if you make a substitution once more, you will find the limit changing to be 0 times infinity. Because once you start substituting, the value of x will be 0, and then 0 is equal to infinity. So instead of having 0 to the power of 0, I changed it to be 0 times infinity, and still I can't use Cauchy or L'Hopital. But also I can find a solution which is e to the power limit x tends to 0, and I will put this function on this form. Lim 2 over x divided by a denominator which is the denominator of the existing denominator. That can be lim 2x over 1 over x. Are you with me, Muhammad? Now if you make a substitution, you will have infinity over infinity. And in that case, or once this has happened, I will try to use Cauchy once more. So the limit will be e to the power of limit x tends to 0. Differentiating, you will have 2 over 2 over x. Differentiating is going to be negative 1 over x to the power of 2. Also simplifying this kernel, which leads to limit x tends to 0, and it's going to be a negative over x squared over x, which will lead to negative x. Still, you have the limit of x tends to 0, but don't forget this is the power. So it's going to be e to the power of 0, which leads to positive 1, as you can see. So, look how many times did we change the value of our limit. Instead of having 0 over 0, we change it to be 0 times infinity, then once more infinity by infinity. And then after differentiating and putting in this form, it's going to be 0 over 0. And then finally, after simplification, you will have your value equal to 0. This is really a very nice problem on the, as I told you, on the use or successful use of Cauchy or L'Hopital theory in dealing with this type of limits, complicated limits. And this is really, we can't use this unless you had, you didn't finish the part of the derivative, so it's an application on the derivative, as you can see. So, once more, I will do them with you with the slides. I think I sent you the PDF supporting this lecture previously. So, once more, if I want to solve it, it's going to be lim x over x to the power of 5. Once you substitute it's infinity over infinity, now I can make the derivative. It's going to be 1 over x over 5x to the power of 4, which is going to be 1 over 5x, which is equal to 0. Same strategy here with x times lim of x. I will make the denominator as a denominator of the existing denominator. Now making the substitution, the condition already exists. I start my derivative, but don't continue without simplifying first. Once we simplify, it's equal to 0, as you can see. If I look to the other problem, which is 2x to the power of x, as I told you, just use the exponential and logarithmic form, which will help you much, and it's ended, as you can see, it's the e to the power of limit x equal to 0, which is gonna equal to 1, as you can see. Remark that we have plenty of ideas of changing the undefined values from one to another, as we saw together in those problems. Those are really very nice problems. You want you to, it's from the list 4.3, you want you to complete or to compute the following limits if they exist. The first of them, if you remark, the first of them is a direct substitution, direct application of the rule. Because mainly once you substitute by infinity, it's going to be lim infinity over infinity. And so, which is infinity over infinity. I will start differentiating and then simplifying and taking the limit. So as I told you, use the rule and simplify for the first one. Right, for the second one, this problem, it's really very close to the problem that we solved earlier. All I have to do, instead of dealing with this form, to put it on the exponential logarithmic function form. So I will do limit x tends to infinity, and instead of dealing with this guy, I will put it to be e to the power of ln x to the power of -1 to the power of x -1, which is simply gonna lead to e to the power of 1 over x times ln of x to the power of -1. Just approximate them together and start making your substitution using infinity. It will be solved directly. The one that I want to go with you in steps is the third one. And the third one is very, very nice. It's an e to the power of 1 plus xy to the power of 2, and that's the sign of the norm. Do you remember what's the norm? Yes, of course, it's the square root of x squared plus y squared. It's the distance between x, y, and 0. Minus e divided by the norm of xy to the power of 4. Remember the norm relation, and then your problem will be a mix between what we studied previously in the previous session, how to manipulate using the advantage of the expansion of Maclaurin or something like this, together with our theory. So I will try to solve in details with you the third problem, which really very tempting. The other two problems, as I told you, they are really very simple. Just try them. You will find them very, very easy. So for this one, it's a 1 plus the norm of x plus for x and y to the power of 2 minus e divided by xy to the power of 4. Also, remember, this limit, it is in R2. The previous two limits were in R1, but it really looks tempting to use the substitution of the polar coordinates, or to use the advantage that I know that R, which equal to the root of x squared y squared. So all I have to do is to change my problem into polar coordinates also. So changing the norm into r squared, as you can see. Doing this, I will have to deal with the limit r tends to 0 for e to the power of 1 plus r squared minus e over r to the power of 4. Of course, if you substitute by r equal to 0, you will have e minus e, which is 0, divided by 0. Now I can use Cauchy and differentiate and so on, or I can use the expansion as I told you previously. Instead of dealing with e to the power of 1 plus r squared, I can put it as e times e to the power of r squared minus e. Then take e as a common. You will have e to the power of r squared minus 1. And then e is just a constant. It will be outside your problem. And I will start to expand this guy. So the first step, as I told you, is to take e as a common, then use Maclaurin, e to the power of r squared minus 1, divided by r4. We did this previously, which is going to be r to the power of 2 plus r to the power of 4 over 2, blah, blah, blah. Take this relation and then make the substitution. Take R2 as a common, and then you will find this is the kernel that we are dealing with. If you take R tends to 0, you will find all of these values will be cancelled because it's related to 0. It will be 0. But this guy will develop at infinity, and so the relation for this function is undefined, as you can see. Or it will be tends to infinity. So once r tends to 0, the result will tends to infinity, as you can see. In this problem in specific. Okay. So once more, this is one of the famous problems dealing with Maclaurin. We already did this in the previous session, but also it's a reminder for you of how to deal with it. You already have the PDF, so I think you are in a very good shape. I will go to the other topic that I want to talk with you about, which is the differentiability of a vector valued function. And of course, Mr. Safe, if you remember, what's a vector valued function? It is the functions running from Rn into Rm. So you have n variables coming in, and you have m variables coming out of this function. And in this function, to be differentiable for those types of functions running from Rn into Rm, to be differentiable, this relation has to exist, and has to be correct. And yes, Mr. Hazem, yes, you are correct. It's exactly like the approximation from R into R, which states that f of x is equal to f of a plus f dash a times x minus a, which is the equation of what's called the approximation of the value of function near a. And yes, Mr. Muhammad, it's exactly the same, the relation that we had previously from R2 into R, which states that f of x and y, in specific, it's going to be f of a and b. If I'm talking about R2, plus the replace, instead of dealing with f dash a, I will use the gradient of the function at a, because I'm in more than one dimension, Muhammad, times the vector, which is x minus a, y minus b, as you can see. And that's, Mr. Safe, a normal shape, which is the value of the function at a and b. But in this case, you have n variables as an input. This is why your function, and also n outputs. So your function in this case, instead of dealing with f of a or f of a plus b, that's the shape of the vector valued function at certain point. Plus, instead of having the derivative or the gradient, we will have the Jacobian, if you remember, the Jacobian of the vector valued function. Mr. Hazen, do you remember the Jacobian? How to get the Jacobian? It's very simple. I will take the first function, and will differentiate it with respect to the input variables. So I will respect this is why you will find f1, for example, the first function, differentiate with respect to x1 to x2, blah, 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 up to xn, because you have n variables. You understand what I'm saying? This is why it's going to be a Jacobian. Times, instead of having x minus a or x minus a, y minus b in 2 dimension, you will have your vector, which connects the main points of x minus a1, or the first component, y minus the second component, and so on. Plus the remainder term. The remainder term that I will take the limit, okay, if you remember, I will take the limit of x of a1, a2, blah, 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 up to an, okay, tends to 0 for the remainder term of a1, a2, blah, 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 up to an, the norm divided by the norm of x1 into x2, x3 minus a1, a2, a3, and that's the limit which should exist and equal to 0. If it exists and equal to 0, it means the remainder will grow smaller as fast, more faster than the values of x approaches the point that you are studying the differentiability at, which means the error term is equal to 0 or tends to 0. This is why I can approximate the function. Bottom line, in vector valued functions, it's exactly the same, like what we had previously in R and R, or from Rn into R. The relation is very, very simple. This is how to discuss the differentiability of vector valued function. It's a generalization of the law that we had previously in one dimension or in dimension. This problem is very, very nice, and as you can see, it will cover the parts that we did go through. Also, Mr. Hazem, if you remember, if you remark, for the function g of x and y, which is running from R2, Mr. Safe, x and y, up to a vector valued function, and the shape of the vector valued function in this manner, it's running to R2, Muhammad. The first component of your vector function, it's the root of x squared plus y squared. the second component is x plus 1. So once more, this is an example of a function g such that running from R2 into R2, as you can see, from f of xy into x plus 1. And the two variables are x and y. So that's the definition of g. He wants you to show that f doesn't have partial derivatives at the zeros. And this is, so this step is really old, this one too, previously covered and the last step also. All I have to do is to do this for the first function and the second function. Since I'm dealing with a vector valued function, I will have to be sure about this with the first one, with the first part and the second one. But before going through, I want you to discuss the differentiability of root of x squared plus y squared, okay, at the origin. And this is really, really simple. All I have to do in order to do this is to start by the partial derivatives. The partial derivatives for this function x squared plus y squared will mean you will do the limit definition of derivative Yazid, which is, if you remember, limit h tends to 0 for f of h minus f at 0 divided by h. That's the main derivative law. But in the case of partial derivatives, means your function will have x and y. So I will do, if I'm differentiating with respect to x, this is going to be the law. Limit h tends to 0, h and limit h tends to 0 for the function of h and 0 minus f at the origin divided by h. That's the law that I'm going to use. If I'm doing the partial derivative with respect to y, the law will be limit k tends to 0 for f0 and k minus f0 and 0 divided by k. That's for finding partial f, partial x, and that's for partial f, partial y. Those are the partial derivatives. So in the previous session, we talked how to discuss the differentiability in one dimension and if I need partial derivative. Of course, Mr. Sif, here I will need partial derivatives. Here I need partial derivatives because your function contains more than one variable. So all I have to do is to apply this law. So once more, as you can see, this is the limit of h tends to 0 over f of h and 0 minus f double 0 over h. Okay, let's do the substitution. So my function f, it is equal to the root of x squared plus y squared. This is why we are dealing with f of x and y. But instead of dealing with f, x, and y, I'm dealing with f, h, and 0. So all I have to do is to substitute. Let's substitute together. So it's going to be f of h and 0, which is the square root of h squared plus 0, which means a square root for h squared. A square root for h squared, it is the absolute of h. And we know the problem with absolute of h. If h is greater than 0, you will have positive h. If h less than 0, you will have negative h. So, which means, if you are trying to study the limit of absolute h over h while h tends to 0, you will be between h over h when h is greater than 0. In this case, it will equal to 1. And negative h over h, which is negative 1, while x is less than 0. Which means the limit doesn't equal to each other. That's the partial derivative with respect to x doesn't exist. It's going to be exactly the same in the case direction or in the y direction. ليه؟ لأنه instead of substituting with h and 0, you would substitute with 0 and k. So your root will be 0 plus k squared, which leads to the square root of k squared, which will lead to the same result. Limit k tends to 0, and you will have absolute of k divided by k, which is going to be once more either k over k, which is 1, or negative k over k, which is negative 1, and the both of them, they are not equal to each other. So once more, the partial derivative doesn't exist. So, as I told you, all I have to do is to study the previous parts, and then you will feel really very comfortable around the discussion. So all I had to do, as I told you, I'm trying to get the partial derivative. Okay, with respect to x, so I will make that change in the x direction. Once you make that change in the x direction, I will take h and 0 and substitute in my function. And the result will be an absolute vertical origin, which means it doesn't exist. We did it plenty of times. A similar debate will be running in the case of your function with respect to 1. But the limit, instead of working with h and 0, remark, I'm working with 1. So it's going to be 0k. So I'm discussing in the other direction. And the same result will be absolute k over k, which is exactly like this guy, which means your partial derivatives doesn't exist. So for the first part, which is asking you to show that f doesn't have partial derivatives, both of them doesn't exist. Okay, Mr. Hazan, if you look to the second requirement, he's asking you, using the results, those results, okay, whatever, if they have derivative or if they have partial derivatives, explain why f is not differentiable. Mainly, it's from the definition. So this question is from the definition. If a function is differentiable, it will have its partial derivatives, but if you don't have partial derivatives, it means your function is not even differentiable. Okay, so why f is not differentiable at the origin? Simple. If a function is differentiable at a point, then all partial derivatives exist. In my case, both partial derivatives doesn't exist. Okay, so it's not differentiable. Okay, this is for the question number 2. For the last part, he's asking you, without further calculation, define the continuity and differentiability domain of G. Without further evaluation, it is really very simple. Look to the value of G. G is a vector valued function. The first component is the root of x squared plus y squared. The second component is x plus y. X plus y is defined for all values in R2. Do you have a denominator or a problem? No. For the root of x squared plus y squared, it is continuous. It's a root function. صح? But it has a problem.